How about some of the equipment here on the ground that you use to talk to and listen to and perform the tracking and control functions?
Okay, I guess what we can do is go over to the other side of the equipment rack here and look at some of the equipment that we have. It is included in this console and in the line of equipment that goes down here on the other side
Good.
of the console.
Let's have a look at some of that equipment.
Okay.
Then.
Okay, yeah, that one. Okay. Okay, what we have here is all of this equipment in this long line is the equipment that we use to control a spacecraft. It is a computer-centered system consisting of two Hewlett-Packard 2100 computers. I think maybe if I start up at this end and just point out some of the major things of interest. One of the most valuable tools that we have in control of the spacecraft are these strip chart recorders. What we're seeing here is a continuous plot, for instance, of the roll and the pitch. This happens to be for the F2 spacecraft. Over right down here we have the F1 spacecraft. That's a period that we're looking at there of about 6 hours worth of data, and as you can see, the spacecraft is sitting there just as steady as a rock over that period of time. This is the roll error that we're seeing there. That is pitch.
What's the period of time represented by the...
about this period here is about 6 hours that we're looking at, somewhere in that.
And what's the step
range.
function there on the chart on the
well,
left?
Notice we were talking about the magnetic roll controller. You see the roll was out here a little way, and the controller pulled it back into the center, and when it got in there, it went off.
Okay. So that's just turning the current off and on.
It's just turning the current off and on, and you see how it just gently eased it back in over a little period of time and pulled it into the center.
What's the jagged curve on the...
Okay, when we were talking about power before, we were talking about the shunt transistors and the power being dissipated in it. That power varies as various loads come on and off. This time of day when we're recharging batteries, the batteries are getting cold, and what you're seeing here is the variation caused by the battery heaters turning on and off.
Yeah.
Also, this line here is the battery state of charge. It's gradually increasing as we get the batteries filled back up again in preparation for tonight's equipment.
The last strip on the right says SAD angle. Now that must be an abbreviation for something which I don't understand.
SAD is solar array drive. This shows the angle of the solar array changing as it keeps the array pointed toward the sun.
Well, what's the step down at the bottom of the chart represent?
Well, the way the digital readout comes down, comes out of the solar array drive, it's in 45-degree increments. It goes 45 degrees, goes back to 0 again, and starts over again at 45 degrees. Okay. We sort it out in the computer.
I see.
Okay, now what we have down here, we have two computers in this system. This one is the data computer that's primarily used in handling telemetry and commands. We're recording all of the digital telemetry data on magnetic tapes. We are checking all of those telemetry limits at all times. We set limits in there to determine if anything goes out of limits. We immediately get a flag, an alarm that tells us that something's going wrong.
Are these tapes then a permanent record of the spacecraft behavior?
Yes, they are. We keep this tape covers every single frame on it, and we have a compressed data tape there that just pulls out those items which are of significant interest that we may keep over a longer period of time.
Right.
In addition to handling the telemetry, this computer also handles the commands going to the spacecraft. The commands themselves are originated in the other computer, which we'll get to in a minute. This unit actually generates the tones under the control of the computer that are sent to the spacecraft. Normally it's operated under computer mode, and we also have the capability of setting in commands manually so that if something happened to the computer, we could still command the spacecraft from this unit. Now we have an additional computer down here which originates the commands and also does some other functions. We use this computer to take the ranging data, or we measure the range to the spacecraft, and we use it to transmit it to a large computer in Dallas, Texas. These computers are not large enough to solve the orbit determination problem, so that computer also functions as a remote terminal to send the data to a large computer. Every time we complete a maneuver, an east-west or north-south maneuver, we range on the spacecraft once every hour from both the station here at Vernon Valley and from the other TT&C station in South Mountain. That data is submitted to the computer in Dallas. We generate an orbit, and then we run a prediction of where we're going to be for the next 3 or 4 weeks and make our judgments on when we have to do another maneuver.
You mentioned another TT&C station. Is it similar to this one?
The other TT&C station is identical to this station. We normally, both of these stations have the capability of controlling up to 3 spacecraft simultaneously. Normally one of the spacecraft is controlled from here, one of the spacecraft is controlled from the other station.
I see.
But we have the capability of either one of them.
You can control both from here, or they can control both from there.
Both from there.
Very good.
And we interchange the spacecraft regularly so that both stations are familiar with both spacecraft.
Okay.
I think maybe in order to understand how we actually interface with the spacecraft, now the controller interfaces with the spacecraft, we might go over here to the control console where the spacecraft controller actually flies the bird.
Let's see how you give some of the commands to the spacecraft, right?
Very well.
Okay. Okay, Archie, tell us about your control center here.
Okay, this is the TT&C control console from which we control the spacecraft. Seated at the console here is Harris Tyre, who's been with RCA for 12 years. I think typical of the kind of experienced people we have flying these birds. He has in this console the various CRTs to monitor all that is going on in the spacecraft, and he also has the capability from this keyboard of transmitting commands to the spacecraft. When we were over at the strip chart recorders a few minutes ago, we noticed that the magnetic roll controller had pulled in the roll on the spacecraft. So what we're going to do now is send a sequence of commands to turn that magnetic roll controller off. What he's doing here is answering a series of questions in there. Now what he's going to do now is to transfer into the computer a command list called roll off, which means to turn off the magnetic roll controller. You want to hold up right there? We'll let him have a look at it. It consists of a series of commands. It's a spacecraft clear command that clears out any noise bits that may have been sent in the spacecraft. What we call a no operation command, which kind of gets the spacecraft's attention. And then the command that actually turns the magnetic roll controller off, followed by a spacecraft clear to clear the command bits out of the spacecraft register so it could not inadvertently be executed again. Now he has brought that canned list in from the disk and is ready to transmit it. Now in order to do it and to safeguard the transmission, he has to answer a series of questions.
Now Archie, the program that you're putting in here is not something that he's making up on the spot, is it?
No, sir. These are permanently stored on disk. They can only be changed or modified by one of the spacecraft analysts or by myself. So it's a system to prevent any unauthorized commands from being sent to the spacecraft.
Okay.
Now, the computer has come in and asked him whether he really wants to clear that list and send it to the spacecraft. So he's going to tell it to clear it. And then having done that, that noise you heard in the background was it printing out and listed it for him. And now he's got to go back and further tell it to unlock the command list, which is what he's doing now. So we get to that point and we're ready to transmit the commands. I think what we'll do now is sweep up to the other monitor where we can actually observe the commands as they go out to the spacecraft. Let it go. Now this takes a few seconds to do because we're there is an actual delay, a built-in delay in the computer, so that even after having answered all those questions, if he decides he didn't really want to send it, he can change his mind. There's the spacecraft clear, just went out. There's the magnetic roll controllers turned off. And we're going to get another spacecraft clear. We'll see the numbers change up here. We just changed again. We got another spacecraft clear. Those noises you could hear in the background are the mechanics of the commands themselves actually going out, the printer running and the receivers getting the verify signal back. So that's how we do it. As you can see, we have quite a few safeguards in this system, so it's virtually impossible to inadvertently do something to the spacecraft.
And when it is done, it's done in a very precise fashion.
It's done in a very precise and controlled fashion. The controller here operates from a daily operating plan that outlines everything that he is to do during the day, which station is to do it, what time he's to do it at, which spacecraft is to go to. They maintain a log at all times when everything is transmitted to the spacecraft. So it's a very tightly controlled operation. We feel we've got a very safe and reliable method of controlling the spacecraft.
That's the impression I get. And we appreciate the tour. Is there anything else you'd like to show us at this point?
Well, I think that's kind of showed you pretty much what goes on here. I think we've showed you generally how we control the bird.
Very, very impressive operation, and we appreciate you taking the time to show it to us, Archie.
Okay.
Thank you very much.
So.
Thank you.
Okay, this is the RCA Vernon Valley installation. The building you see houses the Earth Station serving the New York metropolitan area and one of the two satellite control centers. All the equipment necessary is inside the building. Off to your right, you will see the microwave tower, which is the Vernon Valley terminus of the link into New York City, carrying video and audio traffic on a 3-hop link to and from New York. Halfway down the tower, you may see a weather station that remotes inside the building and keeps us in constant surveillance of rainfall and wind speeds and such. Now we're coming up on our main communications antenna. This is a 43-foot dish with limited motion, which is aimed at the F-2 spacecraft at 119 West. It does have auto track, but it has limited motion. You'll notice a little bit of scaffolding there. It is being equipped at the moment with de-icing equipment. That's a shroud, and it has heating ducts coming into it in order to melt the snow off the lower half of the dish, where in severe conditions it can inhibit the signals a little bit. The tunnel you see that we're following now is a waveguide protector, and it goes over to our other antenna, which again is a 43-foot dish, different type. This one is a precision tracking antenna, which also serves as the communications facility for the F-1 spacecraft. This is a fully movable, fully auto-track antenna which can sweep the whole horizon and is used in that mode during launch to support the spacecraft before they get in a stable condition. This one will track at up to 3 degrees a second and has very precise pointing and provides us with angle information to the nearest hundredth of a degree. We use this information currently to help determine satellite orbits and precise positioning. The house on the back of the dish contains the receivers, the low noise amplifiers which amplify the 4 gig signals. You'll see 2 air conditioners there. They're redundant units to maintain the hot end of the thermoelectric cooling at a reasonable temperature so that the low end can be at its 55 degree Kelvin operating temperature. The counterweights are on this antenna to provide balance for the rapid motion that it's capable of, as I mentioned. The other antenna does not need counterweights because it never moves very far or very fast. The transmitters, of course, are not up in that little house, which is about 6 by 8 feet. They are down in the main building, and the power, the RF, comes to them through the waveguides on about a 60-foot run.